Look closely at the window beside you on an airplane. Near the bottom, you will usually find a tiny hole only a few millimeters wide. On the other side of that window is extremely thin air, more than 10 kilometers above the ground. Inside the cabin, the pressure is kept high enough for people to breathe normally. So why would engineers deliberately place a hole in the window of a pressurized aircraft? Does it allow cabin air to escape? And if that hole were blocked, could the window burst during flight? Surprisingly, this tiny opening does not weaken the window. It helps determine which layer carries the pressure during normal operation, and which layer remains available as a backup. To understand how it works, we need to stop thinking of an airplane window as a single sheet of glass. It is actually a multi-layer structural assembly installed in the wall of an enormous pressure vessel. When an airplane is on the ground, the air pressure inside and outside is nearly equal. As the aircraft climbs, the atmosphere becomes thinner and outside pressure falls, while the pressurization system keeps the cabin at a much higher pressure. That pressure constantly pushes the fuselage outward. People often describe a sudden opening as something being sucked outside, but the real force comes from the higher pressure inside pushing outward. Across one passenger window, the total force can be comparable to the weight of several hundred kilograms. Every time the aircraft climbs, the fuselage expands slightly. When it descends, that load is reduced. This cycle can repeat thousands of times, so the structure must resist both large forces and long-term fatigue. A window creates an opening in the load-bearing skin of the fuselage. Its frame and transparent panels must hold the pressure and transfer the surrounding forces safely back into the aircraft structure. This also explains why modern airplane windows have rounded edges. If a rectangular hole with sharp corners is cut into a stretched sheet of material, stress becomes concentrated at those corners. A crack can begin there and grow with every pressure cycle. A rounded opening allows the load to flow more smoothly around the window instead of concentrating at a single point. But rounded corners alone are not enough. Material thickness, reinforcement, installation details, seals, and the ability to survive a single failure must all work together. The early de Havilland Comet accidents in the 1950s are often simplified into a story about square windows. The real lesson was more complex. Stress, concentration, manufacturing details, and fatigue all contributed. Every opening in a pressure cabin must be designed for repeated loading and must include a safe path when one component fails. That principle appears directly in the layers of the passenger window. The exact construction varies between aircraft, but a typical passenger window can be understood as 3 functional layers. Near the outside of the fuselage is the primary pressure pane. It is commonly made from a strong transparent material such as aviation grade acrylic. During normal flight, this outer structural pane carries most of the pressure difference between the cabin and the atmosphere. Behind it is a second structural pane. This is not simply extra thickness. It provides redundancy. If the primary pane loses its ability to hold pressure, the second pane is designed to maintain the cabin long enough for the flight crew to respond and descend. Closest to the passenger is usually a thin protective panel, often called a scratch pane. It prevents hands, luggage, cleaning equipment, and minor impacts from reaching the more important structural panes. A scratch on this interior cover does not automatically mean that the pressure window has been damaged. Thin air spaces exist between these layers, and this is where the tiny hole becomes important. In a common configuration, the hole is located in the inner structural pane. It is often called a breather hole or bleed hole. It does not create an open passage from the cabin to the sky. Instead, it connects cabin air to the small space between the 2 structural panes. As the airplane climbs and outside pressure falls, cabin air passes through this opening into the space between the panes. The pressure in that space therefore remains close to cabin pressure. The largest pressure difference develops across the outer pane, causing it to carry the main load exactly as intended. If the space between the panes were completely sealed with a fixed amount of air inside, its pressure could change with altitude and temperature. The load might then be divided between the panes in a less predictable way. The breather hole creates a controlled pressure path. Engineers can determine which pane is loaded during normal flight, and which pane remains available as a backup. Imagine the two structural panes as two lines of defense. The opening arranges the pressure so the first line carries the load during normal operation, while the second line remains ready to take over. The hole does not remove the pressure. It controls where that pressure acts. Now imagine that the outer pressure pane develops damage large enough that it can no longer maintain the pressure difference. The pressure in the space between the panes begins to fall, and the load transfers to the inner structural pane. That second pane is designed around a fail-safe principle. Its purpose is not to let the aircraft continue flying normally forever. Its purpose is to prevent one isolated failure from immediately becoming a catastrophe. It gives the crew time to follow the required procedure, reduce altitude, and land the aircraft. This is a central idea in aviation engineering. Designers do not assume that every component will remain perfect forever. A possible single failure must be tolerated without the aircraft losing its function at once. During normal flight, the hole keeps the main load on the outer pane. If that pane can no longer hold pressure, the backup takes over under a condition engineers have already analyzed and tested. Pressure is not the only issue. At cruising altitude, the outside surface of the window is exposed to extremely cold air, while the cabin is warm and contains moisture from the passengers. If moisture becomes trapped between the layers, it can condense or freeze and make the window appear cloudy. The small opening allows the space between the panes to exchange air slowly with the cabin, helping reduce trapped moisture. Its position near the bottom also helps prevent moisture from remaining inside a completely sealed cavity, but this is a secondary benefit. The most important safety function of the hole is still to manage the pressure difference between the structural panes. Saying that it exists only to prevent fogging misses the central mechanism. So what happens if a passenger covers the hole with a finger? The window will not instantly explode. The assembly still has a limited air volume, seals, small clearances, and structural margins. The hole is also not the aircraft's only safety feature. However, deliberately sealing it for an extended period is still a bad idea. Doing so interferes with the pressure balancing and moisture control path that the window was designed to use. In aviation, a component does not need to cause an immediate disaster to be important. If interfering with it moves the system away from a tested condition, it should be left alone. If you notice what appears to be a crack on the layer you can touch, it may only be damage to the protective scratch pane rather than the pressure-bearing structure, but passengers should never try to decide which layer is affected. The correct response is to inform a flight attendant so the crew can have it inspected according to procedure. The tiny hole in an airplane window does not defeat pressure through strength. It does something more subtle. It controls where the pressure acts. By connecting the cabin to the space between the structural panes, it makes the outer pane carry the normal load, preserves the next pane as a backup, and also helps limit moisture between the layers. Around, it is a complete system of strong transparent materials, rounded frames, seals, reinforcement, and fail-safe design. So the next time you look through an airplane window at cruising altitude, notice the tiny opening near the bottom. It is a perfect example of how aviation engineering works. A detail that is almost invisible, placed in exactly the right location to control a force acting across the entire aircraft. It is not a hole in the safety system. It is the feature that tells the system exactly how to carry the pressure.